Hello everyone, I am Amir Irani from Waikato Hospital, Hamilton, New Zealand. I want to talk about the molecular dynamic simulation that we have done about Sugammadex and its interaction with some muscle relaxants. So it's a structure of Sugammadex. It has 8 sugar rings and with some side chains. And here is a 3D diamond, 3D structure of the Sugammadex. It has one side as a hydrophilic side with several hydroxyl group here, and it has a cavity which is hydrophilic. We have done simulation with several kinds of drugs, but we are more focused on the rocuronium and rocuronium in this time. I've done some docking process to get affinity number for all of those drugs, and this negative number here is related to the affinity of those drugs with the Sugammadex. So more negative number, it's more stable combination, like for example here for the rocuronium, which we have negative 7.4 in comparison with propofol, where we have negative 4.5. And so it's telling us, so this combination is more stable because it has less energy. But those numbers are related to the docking process, where we consider the structure of the Sugammadex as a rigid molecule. So to get more realistic, more acceptable number, we needed to run molecular dynamic simulation to include the dynamics of those drugs and Sugammadex. We have done a 5 nanoseconds simulation for each drug, and we've calculated the change in enthalpy for each of them, and then compared them with the available experimental result from the literature, and we've got a good correlation between our molecular dynamic simulation and experimental results available in the literature, which has a logarithmic relation. So this is kind of validation of our simulation, and we understood that in this way we can get more information from this encapsulation process. So to get more details, we have run a long simulation, actually several of them. So we have done 4 simulations with the length of 500 nanoseconds, and so we've monitored the distance between drug and Sugammadex, and we have seen that after about 100 nanoseconds, and for example for rocuronium, so it goes into the cavity, entering from the hydrophilic side, and then after 100 nanoseconds it remains in the Sugammadex for the rest of the simulation. It's happening for the rocuronium as well, but the rocuronium has more freedom, and we know that the rocuronium has less affinity to Sugammadex. So this simulation also shows that rocuronium has more freedom to going around, and it takes more time for some of them going into the Sugammadex. But it's still the same as rocuronium. When it goes into the rocuronium, it still remains there. To understand why it's happening, I've looked at the number of the hydrogen bonds for the rocuronium when the rocuronium goes into the cavity. So you can see here the number of hydrogen bonds are really much more than the number of the hydrogen bonds in comparison with the rocuronium. So this is the simulation that we have done. It shows how the drugs interact with each other till sometimes they find each other possible to encapsulate for the encapsulation. So they try to jiggle around and find the more stable connection till rocuronium reach the hydrophilic side. So it takes some time for them to be able to come into the cavity. So still though, looking for the entrance. And yeah, so this kind of interaction from side is not stable, and you can see here. Here is where the recurrenium went to the hydrophilic side, and then it goes into the cavity right now, and it's still, and it remains for the rest of the simulation. This is the this kind of simulation gives us more details of how it's this encapsulation happening, and for further studies, when we want to develop more drugs, we can use those simulations. Thank you for your time.